A number is in scientific notation if it's of the form a times 10 to a power of n, where the number a is between 1 and 10, possibly equaling 1 but not including 10, and n represents any integer. So by that I mean n could be 0, 1, 2, and 3, and so on, but it could also be negative numbers too, like -1, -2, -3. So if we look at the very first example, we have 5 times 10 to the power of 3. So this number is definitely in scientific notation. If we look at 5, that's the number that goes in place of a. Okay, that's definitely between 1 and 10, so that's good. And n is equal to 3, which is an integer, so this number is in scientific notation. Maybe to understand what it is equal to, we can write it from scientific notation into a decimal form. So 5 times 10 to the power of 3 means take 5 and multiply it by 1,000. And that takes the value 5 and puts 3 zeros on the end. So if you say 5 times 10 to the power of 3, that's the same thing as saying 5,000. One way to think about this is there is a decimal after the 5, and the number 3 moves the decimal points 1, 2, 3 places. So it's very easy to go from scientific notation to decimal form. It's just a matter of locating the decimal point and moving the decimal sum number of places. Let's compare this to 1.5 times 10 to the power of -5. So this number is also in scientific notation because the number a, 1.5, is between 1 and 10, no problems there, and n equals -5 is an integer. So this number is definitely in scientific notation. If I want to write this in decimal form, this means 1.5, and if you remember how we defined a negative exponent, it means divide by this number instead of multiply by it. So this would be divided by 10 to the 5th. So if you see a negative exponent, here it was positive, it meant multiply. Here it was negative, so we're actually dividing. 10 to the 5th means a 1 followed by 1, 2, 3, 4, 5 zeros. And the net result here is going to be moving the decimal point on 1.5 5 places to the left. And we should have this value here. So the decimal point started between the 1 and the 5. By dividing by 10 to the 5th, it goes 1, 2, 3, 4, 5 places to the left. So here's the number in scientific notation, and here it is in decimal form. And just really quick, looking at the last two examples at the bottom. So these two numbers are not in scientific notation if you're being technical about it. Here a is equal to 75.1, and this is not between 1 and 10. And in fact, it is greater than 10. So even though it kind of looks like it is in scientific notation, the problem is this value here is greater than 10. Likewise for this second example, okay, here a is equal to 0.6. And the issue with this is that the value a, it's less than 1. So it's not in this interval from 1 to 10. So technically these two look really close to scientific notation. They're just not expressed in the form exactly. In this example, I want to take the following numbers and write them in scientific notation. Let's start with this very first one here. It's in decimal form, and we need to figure out two things. What is a, and what is n? So the choice for a should be a number between 1 and 10, and I think an obvious choice for this problem is 2. So basically I'm just looking at my number and saying, okay, if I had 2, everything else can be written as 10 to a power of n. So second step is, well, what is n equal to? I don't know that. But we can easily figure it out by counting, okay, how far do I have to go from the decimal point to being next to this 2 here? I can count the number of zeros, so that's 3, 6, 9, 12. The value for n is 12. This means that my answer to writing this number in scientific notation is 2 times 10 to the power of 12. And here we can ask ourselves if we think the answer makes sense. What would happen is the decimal point on 2 is located right here, and multiplying by 10 to the 12th power makes this bigger. And in fact, it is moving the decimal point 12 places to the right. So this value would certainly match up with this, and it meets all the requirements. A, which is 2, is between 1 and 10, and 12 is an integer. Okay, if we check this out in the next one, again, we have a number in decimal form, and the idea is, well, can I figure out A, and then can I figure out n? So I see that there's a 45 here, and it might be tempting to say, well, okay, A should be equal to 45, but there's a problem with choosing this, so this would not be the correct answer. 45 is greater than 10. I instead want a number between 1 and 10. So instead, I'm going to choose 4.5. So the second step would be, okay, well, how many times do I have to move the decimal to go from this spot here to between the 4 and the 5? So let's count it. 1, 2, 3, 4, 5, 6, 7, 8 places. So it's like, okay, the decimal moved a total of 8 times. But I know that the number is getting smaller, so here's why I want to use a negative 8 instead of a positive 8. The answer to this part is going to be 4.5 times 10 to the power of negative 8. And again, just like take a step back and say, well, is this in fact correct? If I take this number, and the negative means I'm actually dividing by tens, this number is going to get smaller, so the decimal point is moving towards the left. So this is the correct answer for writing this number in decimal form to this in scientific notation. And for the last two here, these are really close to being in scientific notation. The issue is, it looks like we're trying to use A is equal to 75.1, but that's no good. Again, that's a number that's bigger than 10, so this is a problem. Instead, I would like to use, well, yeah, if I could just move that decimal one place this way, I get 7.51, and that would be an acceptable choice of A, so I'd rather use this. So how are we going to fix that within the original problem? So let's do a little bit of work here. I'm first going to change this number so it's in decimal form. And to do that, I take the 7, 5, and the 1, and I move this decimal 3 places to the right. And it would end up with this number here. I would have the decimal going 1, 2, 3 places. And so the answer in decimal notation is 75,100. But now to convert this thing into scientific notation, if we use 7.51 as our value for A, you just have to know, well, what is the power that goes on 10? So what should n be equal to? And we can count it. It's 1, 2, 3. Well, it's actually 4. So it'd be kind of nice if we didn't have to do all this work in the middle. We could have somehow just like looked at where the decimal is located and adjusted the exponent. And here's the way I see it. The problem with this is the decimal was moving 3 places to the right, but it's not sitting in a good location. It really should be right here. If you placed the number, the decimal here, that really means you have to go a total of 1 extra than 3, which is 4. When I look at this problem, I can go from this to this almost. So said another way, we made this number smaller, so we had to make the exponent bigger. Let's try this idea in our very last example. So let's see. Again, the problem here is we're trying to use A is equal to 0.6, but that's no good. That's something that's less than 1. I mean, really, I'd like to use A is equal to 6 by moving this decimal one place this way. Okay, so to figure this out, let's take the same approach of taking 0.6 times 10 to the negative 4 and writing it in decimal form. We're going to move the decimal point 4 places to the left. that is, we get 0.1234 zeros. So it started here, and we went 1, 2, 3, 4 places to the left. So if we want to now convert this into scientific notation using 6, as an exponent, we have to go 1, 2, 3, 4, 5 places. So this is the new value of n is equal to 5. So said another way, okay, I made this bigger. To balance things out, I'd have to make this 1 smaller. So since this went to positive 6, that's bigger, here I have to make this smaller by 1, dropping it down to 5. For example 2, I wanted to look at why you might want to use scientific notation. So I have a picture of a solved Rubik's Cube, and here's a scrambled one right below. When this puzzle came out in 1980, it was advertised as saying there are more than 3 billion ways to scramble this cube into something that looks like this. And there's only one solution out of all these possible combinations. So 3 billion is, it's a big number. It's not that hard to write out, but if we convert this into scientific notation, that is going to be 3 times 10 to the power of, and we just have to count how many zeros there are, and there's a total of 9. So scientific notation is useful when you're dealing with a very large number or a very small number. If the numbers keep getting bigger and bigger and bigger, this is a more concise way to express that answer. So anyways, the Rubik's Cube was advertised as having more than this number of possible ways to scramble it, and then again, only just one potential solution. So the actual number of ways to scramble a Rubik's Cube is the following. It's 43 quintillion, 252 quadrillion, 3,274,000,000,000, 489,856,000. Like that's the actual number of ways you can scramble a Rubik's Cube. And, maybe just an approximation of this would be, well, there's a 43 followed by this many zeros. And you would read this number as 43 quintillion. So, goes to thousands, millions, billions, trillions, quadrillions, and then quintillions. So that's a huge number. So it's nice to just approximate it like this. Instead of writing this whole number out, if you just want to approximate the number of solutions, it would be more concise to say, okay, well, I can use 4.3 as my value for A, and just count the number of times that I move the decimal point, which would be 3, 6, 9, 12, 15, 18, and then one more would give me 19. So in scientific notation, it's just easier to compare what the original value was here to this really large one. And really just by focusing on the exponents, like up here, n was equal to 9, and down here, n is equal to 19. And that is much bigger. There's no need to really list out the value in decimal form. You can just say, oh, well, I have 9 zeros on one. There's, well, really only 18 zeros on the other, but it is much, much larger.